Hello from the Forcetronics YouTube channel. Welcome to designing a thermocouple-based temperature measurement circuit, and this will be part one in a two-part series. So that's what we're going to talk about, making temperature measurements using thermocouple-based temperature sensors or technologies. Before I get started, check out Forcetronics.com for Forcetronics services, whether it's design services or training services. Also, check me out on social media. If you haven't subscribed to the YouTube channel, please do. And if you like what you see on this video, even if you're a subscriber or not a subscriber, just hit the thumbs up. It really helps out on the videos, and I put a lot of time in that, so I'd really appreciate it. All right, with that said, let's get started. Okay, here's what we're going to cover in part one and two. So part one is going to be an overview into what is thermocouple, what is the theory behind it that allows thermocouples to be a way to measure temperature. We'll talk about some of the pros and cons of thermocouple. There's some clear applications where you want to use thermocouples, and then there's some clear applications where you don't. Then I'll provide an overview of setting up, a circuit and some of the considerations when setting up a circuit to measure thermocouple, because thermocouple is a very sensitive type measurement. So we'll talk about that from a high level, and we'll even talk about the calculations and things like that in software. And then part two, we're really going to dive into a real world circuit. So I won't be looking at a block diagram. I'll show you a real schematic that I did, some of the things I learned, mistakes made, things that I did right, things that I corrected. So you can learn from some of my mistakes to speed up your process, my mistakes over the years. So yeah, that's the plan for parts one and two. Let's dive into what are thermocouple measurements and what is the theory behind it. So the thermocouple measurements is based off the Seebeck effect. And the idea here is if you put two dissimilar metals together in a closed loop, you will get current flow. And if the two metals aren't in a closed loop, maybe they just have one end connected and the two ends are open, you should have a voltage there. And so the Seebeck effect can be used in various areas, but where it's useful for temperature and where the term thermocouple comes from is the amount of current or the amount of voltage that's generated from joining these two dissimilar metals together is proportional or will change with temperature. So that's the basis of a thermocouple measurement is we're putting two dissimilar metals together. It automatically, through physics, I'm not going to get into the physics because I don't know, but it basically causes a current flow, and that current flow will vary with temperature. If we could somehow measure the voltage at the end of these two dissimilar metals that are connected together, we could use that to help determine the temperature. The problem is, though, is to make that measurement, you have to connect those two thermocouple wires, and we'll talk about what type of metals are used for thermocouples and the different types, but you have to join them to some kind of connector or to some kind of other wires or to some other kind of PCB trace so you can measure them. Well, guess what? Once you join those two dissimilar metals to more metals, then you get another Seebeck effect. So if you look at the diagram on the bottom, so T1 is showing the point at which two metals, metal A and metal B, are joined together. So in a thermocouple measurement, that point T1 would be where you're measuring temperature at. So whatever you're trying to measure temperature of, that's where the T1 point would be. Now, T2, and that's often called the measuring junction or the hot junction. And then T2 is where you're joining to whatever measurement connectors you're using. And so what they're trying to show is C is meant to be, copper, maybe in a PCB trace or some kind of aluminum connectors or whatever. And T2 is called the cold junction or the reference junction. And I'm going to talk a lot more about the reference junction, but for me, when I was learning about thermocouple theory, this was the hardest part to realize, at least for me, to connect the dots in my head. But it's important to note a thermocouple measurement is really just a differential measurement. And so T2, our reference point, our reference junction, we have to know either the thermocouple effects of joining the metal there or the temperature at the reference point, and we use that understanding of the reference point and the voltage coming in from T1 to determine what the temperature is at T1. Okay, and we're going to talk a lot more about that. Okay, so You can join any two dissimilar metals together to get this Seebeck effect, but for thermocouple purposes, they've sort of standardized on a couple different types of thermocouples, and they use these letter designations for them. And here's a chart, and these are the most common ones, and they're also trying to show typically when you buy this wire or these thermocouple probes at the store or online, they typically come in these color formats, and that's what they're showing. And so the two most common ones, and the two I have the most experience with, are K-type thermocouple and J-type thermocouple. There's much more, but the most common are K-type and J-type. And for our example in part 2, and in this part, I'll talk more about K-type, but the principles apply to all of them. And you can see the two metal alloys in K-type are nickel chromium and nickel aluminum. And if you look over here, you can actually see one of the benefits of thermocouples, and that's its ability to measure very high or low temperatures and its measurement range. And I'm going to talk more about the pros and cons, but that's one of the major, that is the major benefit of thermocouples, is they have such a wide temperature measurement range. Okay, and that's a good lead into the pros and cons. As I just stated, and I'll restate it, the two main benefits, in my opinion, are extreme temperatures. I can measure, down to negative 200 or negative 270 degrees Celsius with K-type, and up to, I forget the top of my head, but I think it was plus 1300 degrees Celsius. Not only is 1300 degrees Celsius very high, but that's such a huge range, right? Imagine trying to measure that. How would you measure that with, a lot of times in the hobbyist world or even in the engineering world, if you're just measuring an ambient temperature and down to freezing and maybe up to, 100 degrees Fahrenheit, you can use these, simple ICs. But those ICs would be destroyed if they tried to measure 1/3 or maybe even 1/4 of the temperature range that thermocouples can cover. So that's their main benefit. And they're also pretty rugged, right? Because it's two metals joined. So if they get dirty or if they get stepped on, they're not necessarily going to break. And you can buy thermocouples where it's just the bare two metals exposed, at a junction welded together. But you can also buy them in probes that are protected. And a lot of time, the limitation of the temperature range you want to measure is not the thermocouple. It's the material that's housing the thermocouple. So sometimes you can't get the whole range of a thermocouple just because the probe housing can't handle the whole range. And of course, if you want to go up to the highest range, the probe housing gets more and more expensive. Okay, what are some of the cons? Well, as we're going to see, thermocouples, the Seebeck effect doesn't have a high current flow or high voltage. So these are very sensitive measurements at very low voltage levels. And we'll look at some examples. But they're susceptible to noise. If you have any errors in your measurement range, it can throw you off multiple degrees in a thermocouple measurement. Thermocouples can corrode over time just because they're exposed to harsh environments. The accuracy is not great, and that relates to the sensitive measurement. It also relates to the reference point, which we'll look at later. But not great accuracy. I mean, unless you're making a precision instrument, you're the best you're going to do is out plus or minus 2 degrees Celsius accuracy. And then this is less of a con, but thermocouple, a lot of the ranges are linear, so it makes the calculation easier. But then there's also non-linear parts of the thermocouple range, which you have to use polynomials or a lookup table for. But once again, the pros is why you would use thermocouples. If you're just measuring room temperature in your house or the temperature outside in your garden, you probably don't want thermocouples. It's for very harsh environments. So if you're designing your own reflow oven or you want to monitor your oven at your house, that's where thermocouples come into play. Those type of things. Or maybe you're designing a electric power go-kart and you want to measure engine characteristics in a harsh environment. That might be a good application for thermocouple. Okay, I wanted to give you an idea of the curves and some of the Seebeck coefficients to kind of show you how sensitive they are. So if we start the curve on the right, you can see some of the different types. Once again, I'll be focusing a lot on K-type. You can see the curve in green. you can see that we have voltage in millivolts. So this is a millivolt level measurement, but really you need tens of microvolt resolution to discern 1 degree to the next. And you can kind of see temperature on the X and voltage on the Y. You can see that these curves are fairly linear. Now, if it's linear, that just means like, oh, every degree goes up, I don't know, 10 microvolts. But there's also areas that are not linear over here, and I think they're not even showing some of the higher ranges, which may not be linear. So those make the calculations a little more trickier. And then even you can kind of see in the linear region, what is the Seebeck coefficient? And look, we're in tens of microvolts, right? So that's a very tough measurement. If you tried, let's say you had the best noise canceling and you had this clean signal, you couldn't use a 10-bit ADC to measure to discern 1 degree from the next. It doesn't have enough resolution. I don't even think a 12-bit one would either. So you need very good measurement capabilities, which we'll talk about. And one last thing I'll mention is these curves and these coefficients. They're often maintained by a standard or national lab in a particular country. So I'm in the US, so NIST, or the National Institute of Standard Technology, they're the ones that define what the thermocouple curve is and what the Seebeck coefficient, and the reason is they define it on this level is, they want to have a standard place to define it so that everybody's using the same system. And you can go to the NIST website and look up information on thermocouples and things like that. Okay. This is where we're going to be probably spending the rest of the tutorial on is a high-level diagram of how the measurement's made using hardware as well as the calculations in software. You should notice this part. This looks like a lot like the first picture we saw, right? This is our hot or measurement junction where we're measuring temperature. And so if we're talking about K-type, this is our nickel chromium and nickel aluminum wires. Here's our reference junction. And this is going to be an important part of the measurement. Then I mentioned how the voltage is very low. Well, you're typically going to want to amplify that because you can't resolve it with standard ADCs. I mean, you can get very high resolution ADCs, but so an instrumentation amplifier. So an op-amp, an instrumentation amplifier is a type of op-amp that has very low noise, very low drift. It's made for high precision measurement applications. We have an ADC, and then a microcontroller to take that data along with the temperature at our reference point to get the resulting temperature. And I'll talk more about this in detail. I'm just kind of going through the whole thing, but it's important to note we have to know the temperature at our reference point because that is going to affect what the error correction of the voltage coming from the thermocouples. And the reason is our reference point is where the thermocouples meet another dissimilar metal, right? And so we need to understand what's going on at that reference point to correct the error to get the real voltage coming from the thermocouple wires, and also to establish our reference point, which is sort of the same thing. It's an important thing to note, though, that all these thermocouple equations and calculations, the reference point is, when they're done, they base the reference point off of 0 degrees Celsius or 32 degrees Fahrenheit, freezing. So let me bring up a picture. This will help explain what the reference point's all about. So if you wanted to make a better accurate, a high accuracy thermocouple, it seems weird saying high accuracy thermocouple, but an accurate thermocouple measurement, you often use an ice bath. So this is often used for calibration of thermocouples and things like that. But the idea is all the NIST curves and the NIST data, the National Institute of Standard Technology, bases this off a 0-point reference. So what that means is when you get the Seebeck effect and the current flow, if you use 0 degrees as your reference, then that means there's no error. You'll get the actual Seebeck voltage out of the thermocouples, and it's directly applicable to the tables or to the equations that the national labs set up. So you can see two examples, right? So here is a drawing, and our reference point is the ice bath. So they're filling it with ice, and then they fill it with a little water, but the idea is it should be at 0 degrees Celsius or 0 degrees Fahrenheit. And then you can kind of see a real world picture where they have multiple thermocouples in there. Now this makes a very clean way to do it. Now you're still getting a low voltage signal here, so you still need to amplify it and measure it. But the idea though is the ice bath as a reference point is not very practical, if you're trying to do it in your house or in an industrial environment. So with that sort of background on the reference point, the idea is this is most likely not going to be 0 volts. And this could actually vary, over time if your circuit maybe is slowly heating up or cooling down based on the weather outside. So what we need is we need to measure the ambient temperature at the reference point, and there's an error correction we'll do, and I'll talk about that in a second. And then of course the instrumentation amplifier is going to have some type of gain. So we need to know the gain because that gain changes the voltage that's coming out of here. So we have 2 error corrections, right? We have the reference point correction, the gain correction to get what is the real voltage coming out of the thermocouple wires. Now this is a high level circuit. Now, and there's other ways to make this measurement, but this is sort of the most common today as far as I know. So I mentioned the low voltage levels, which I already talked about. Some things that are not shown in the block diagram is you often need filtering or just smart noise reduction techniques. So for instance, you wouldn't put this near a switching power supply on your circuit because a switching power supply is very noisy. You probably want to isolate your ground plane on your PCB layout, things like that to reduce noise. And I'll talk about that more in part 2. And this is what we'll use in part 2. There's also ICs out there that combine these blocks and actually do a lot of the calculation for you. So here I'm going to do more of a theoretical step through of how everything's done. But then in part 2, we'll see we can get some components, some ICs that handle some of this harder stuff for us. So that's what we'll look at in part 2. But let's talk about now. We just did a brief overview of the hardware. Let's talk about how the temperature is actually calculated. So I'm going to talk about some of these abbreviations I have here. So VTC is the thermocouple voltage. So that is the voltage caused by the Seebeck effect. Then we have VRJ, which is the reference junction voltage. This is something we won't actually measure directly, but it's the voltage caused by the fact that you have the Seebeck effect. You have metals joining a connector that's also made of metal, and so we have to take that error out. Vout is going to be the output voltage of the amplifier, and then AG is going to be the gain of the amplifier. And just to let you know, once we get the voltage here, we can use the equations from the national laboratories or the lookup tables to get the temperature, and that's kind of what I'm showing with this function. And then we're not going to be able to measure the VRJ directly, so what we do is we measure the temperature, and there's a function out there to get to the voltage. I'm sorry, I have to view this in the non-slideshow way to show this equation. But anyway, so the voltage at the thermocouple is going to be equal to Vout divided by the gain of the amplifier, right? Then we need to get rid of the error. So we're adding the voltage at the reference, which we can't measure directly, but we can derive. And we derive it using the temperature, and that's how we get V thermocouple. And then there's ways to then get the temperature. Okay, so let's take a look at some of these lookup tables. So here is a PDF lookup table for K-type thermocouple measurements in Fahrenheit. So if we look here, we can say 50 degrees Fahrenheit, we should have this volts in millivolts, right? So 397 microvolts. And then if it's 51, it'll be 419, 52, so on and so forth. And you can see that 10, which is 60, 619 is the same here, 619. So you can see how you read this table. Now, so one thing we could do is if we get the thermocouple voltage, we can use this lookup table, which you could have, in an array or something like that to look up what the temperature is, right? And they have this whole lookup table through here. Now, we don't have to use the lookup table. We could use a polynomial. And once again, these are defined by NIST in the US. And you can see it here on the website there. They mention NIST. This is a Mosaic website, documentation web. It's great. But here is the K-type equation, right? So these are pretty big equations. And these coefficients are what they establish to fit the curve that they measure in a laboratory high accuracy setting. Some of these values, like the thermocouple voltage, is V, and then VO, TO, P1, P2, these are all coefficients that are derived to fit the curve of the thermocouple measurements in the laboratory setting. So you could, instead of having a lookup table, you could use these equations. Note that the equations here only apply for certain parts of the range. So you may not even be able to cover the range with these equations. You may have to look up other equations. And then finally, what I wanted to show you is they have a similar thing for getting the voltage at the cold junction or the reference junction. So remember, we can't really directly measure the voltage, so we can only measure the temperature. And so TCJ is the temperature at the reference junction. And then once again, we have these coefficients we can plug into this equation to get the voltage at the reference junction. So once we've done all that, whether using a lookup table for the K-type and then the polynomial for the reference junction, or using both the formulas for the reference junction and for converting the voltage of the thermocouple, we can finally get to our resulting temperature. Right, so that's not easy. That's a lot of work. The good news is we'll see in part 2 that we have integrated ICs that do this for us. Also, the benefit is if you're using the thermocouple within its linear range, then these calculations become much easier. But if you do want to use it out of its nonlinear range, even if you're using some of these off-the-shelf ICs, you still have to do some of this math in your microprocessor or microcontroller. Okay, that's it for part 1. In part 2, we're going to look at a real circuit. We're going to show some measurement examples. We're going to show some sources of error that you want to watch out for and keep in mind. And when I say we're going to look at a circuit, we're going to look at everything from the parts, how to configure them, as well as the PCB layout, and even some of the calculations in software. So we're going to look at the whole we looked at more of a high-level theory way of doing it. Now we're going to look at a practical way to do it in part 2. Thermocouples are, a complex subject, so if there's anything I missed or if there's any questions, use the comment section. And once again, if you like what you saw, hit the thumbs up, and I'll see you back for part 2. Thank you for watching.